All right, then let's start today by doing a review of something that we saw at the end of Friday's lecture. So, real simple fill in the blank question here. Which second row element prefers to make a -2 ion? All I need from you is the symbol of that element. So go. Right, first thing that we want to think about, we're talking about the second row. Second row is period number 2. So we are looking at one of these 8 elements. So last chance, get something in. All right, so correct answer here is oxygen. Now, to answer that question, we had to go back to, again, this is where we ended Friday's lecture. We're talking about common charges. And so first thing that we should know is, again, we're talking about period 2. So it's got to be one of these 8 elements here. And since it's a negative charge, we know it's a nonmetal. Nonmetals are the ones that have negative charges. So we're automatically on the right-hand side of the table. We have to remember that charges count backwards. The noble gases have no charge. And then we count from there. -1 for the halogens, -2 for the chalcogens, -3 for the nitrogen group. And then we start getting to either the elements that don't make ions or make very few in group 4A, group 14, and metals after that. So we're looking for group 16. Group 16, row 2 would be oxygen. So the correct answer there was O. So where we're putting our focus today is looking at our methods of counting. And so where we're going to run into some issues, I guess you would say, is that thus far we have focused on the individual atom. We have focused on the individual molecule. And the problem with those is that individual atoms and individual molecules don't really amount to things that we can count very easily. There are more there are more water molecules in a teaspoon of water than there are teaspoons of water in the ocean. We're dealing with a scale issue here that is not insubstantial. And so because of that, counting by atom, counting by molecule is not something that we can do very easily. And that's one of the reasons why we use instruments. We use balances and calculate mass. We use volumetric glassware like graduated cylinders, burettes, pipettes. Why do we do all of that? Because that stuff's a lot easier to measure up here on the scale where we live. We call that the macroscopic scale. Down at the microscopic and submicroscopic level, where we have all those individual atoms, it's a lot more difficult because there's a lot more stuff there. So what we do instead is we have figured out a way to define some terms. And one of the terms that we have defined is that of the mole. So a mole of objects contains what is called Avogadro's number of those objects. Avogadro's number being 6.022 times 10 to the 23rd. Now, with Avogadro's number in mind, we can start to see why we have such a problem with this idea of scale here. I can't think of a single thing that I know that there are Avogadro's number of here on planet Earth that would be anything that I could tangibly talk to you about. Because let's just do the math in our head here. 10 to the 6th is a million. Well, that means that 10 to the 9th is a billion. 10 to the 12th is a trillion. 10 to the 15th is a quadrillion. 10 to the 18th is a pentillion. 10 to the 21st is a sextillion. Yeah, we're talking about 602 sextillion objects. I don't know what that looks like. I can't put that into terms that we would naturally think of. I can't think of what, 600 sextillion dollars looks like. That's more money than that exists in the world. So this is why we have the mole. The mole helps to contextualize that a little bit for us by saying, okay, yeah, that's a big pile of stuff over there. Let's put that into a number we can actually understand. It's 0.5 moles. Oh, okay, I know, half a mole, sure. Rationally speaking, I don't know what that means in terms of atoms. It's more atoms than I could ever count in my lifetime, but I know what a half is. So that's where we're going to get context. So a mole of objects contains Avogadro's number of those objects. And so if we're thinking about things from a conversion kind of standpoint, this is going to allow us to do some simple conversions in the same kind of way we did conversions in module number 1. I can take my unit in the numerator, cancel it out by putting that same unit in the denominator of my conversion factor, and those two units will cancel each other out and give me the unit that I want. So if I already have atoms, I divide by Avogadro's number and can turn those atoms into moles. If I already have moles, I can multiply by Avogadro's number. The moles cancel out. Then I'd be left with atoms. And so through the use of the mole, I have a way of bridging something that I can't quite fathom in terms of the number and magnitude to something that I at least have a way of contextualizing. Now, again, I don't know exactly what a mole is. I just know it's a way of condensing that number into something more tangible. To complete the journey to something that we can actually contextualize, we need to bring in one other concept. So here's the concept of Avogadro's number. Let's bring in the concept of molar mass. In molar mass, we have another bridge. The bridge here is between the concept of the mole, which again, we don't fully understand other than it just helps us shrink that number down, to something that we can actually measure. We can measure grams. We can use density and volume to turn milliliters into grams in just the same way. So I can measure those things. Molar mass tells me exactly how much 1 mole of an object weighs. Now, for elemental samples, that molar mass also comes directly from the periodic table. So what this sets up for us is a very convenient conversion where I can use AMUs, atomic mass units, to talk about the mass of an individual atom, or I can use grams to talk about the mass of a mole of those atoms. So 1 atom of helium weighs 4 AMUs. Avogadro's number, 1 mole of helium atoms, weighs 4 grams. The number is the same. The unit just changes based upon, are we talking about the macroscopic world where I'm measuring in grams? Or am I talking about the microscopic world where I'm measuring in AMUs? The number's the same either way. I just changed the unit to whatever it is that I'm focusing on. But I can set up a conversion factor in exactly the same way. If I want to turn grams into moles, I can divide by that molar mass. Grams end up canceling. I'm left with moles. If I want to turn moles into grams, I can take that molar mass and multiply it. The moles cancel out. I'm left with grams. So what works out for me here is I now have 2 ways of converting things that I want to know into this interior unit of the mole. Well, I can use my general properties of math. If A is equal to B and B is equal to C, I can make A equal to C as well. I just have to link them together properly. The real utility of moles is that they allow us to be that thing that goes from the microscopic world to the macroscopic world. They tie both of those ends together. So I can go from number of particles to the mass of those things using moles as that intermediary between them. So if I want to figure out how many atoms there are, switch that, go to moles, take the moles and turn it into grams. If I want to figure out how many molecules are in a sample of this compound, I can weigh the compound out, use the molar mass to turn the grams into moles, use Avogadro's number to turn the moles into molecules. They all tie together. And so that's really why we use moles. It has nothing to do with it being a unit that is, particularly special or great. What it does for us is it standardizes things. It says, okay, this is the standard. Avogadro's number of particles. So when I look at molar mass, here is the number of particles that I need to look at, and now I can weigh that out on my scale. And so as I was saying before, that standardization is ultimately what is going to allow us to do things like empirical formulas this week, where by stating what the number of moles is, I know that that moles directly correlates to a number of particles. And so I can use the mole ratio, which is a lot smaller, as a stand-in for particle ratio, which would be a lot bigger. So instead of saying there are 3 times 10 to the 30th atoms of carbon and 3 times 10 to the 30th atoms of iron, I can look at them and say, oh, there's the same number of moles of each of them. They're related in a 1-to-1 ratio. That must be its empirical formula, 1-to-1. All right, so this first question is a top hat question, but we are going to do it together. And then I'm going to let you try a different one on your own here. So the question is this: how many milligrams of phosphorus are in a sample that contains 10 to the 30th phosphorus atoms? Now, one thing that I strongly encourage you to do when you're setting up problems like this, take that first couple of seconds and just organize yourself and try to figure out, how do I get from what I am starting with to what I'm being asked to do? Because if you don't take that organizational step, what happens is you end up getting confused a lot of the time, and you do extra conversions that you don't need. And sometimes those extra conversions cancel out and you get to where you're supposed to anyway. Sometimes they don't, and you end up in the complete wrong place. So we are starting with atoms. And we want to take that all the way to milligrams. So I know I'm going from microscopic atoms to macroscopic mass. The only way to connect those two is through moles. So the first conversion I need to do is to turn those atoms into moles. And so starting with my 10 to the 30th, and I'm going to add a 1 times here just to give us proper scientific notation. I've got 1 times 10 to the 30th atoms of phosphorus. My first step is to convert those atoms into moles. For this, I'm going to need Avogadro's number. Avogadro's number, 6.022 times 10 to the 23rd atoms in 1 mole. And so my atoms end up canceling out. Notice I didn't cancel out the phosphorus. I could. But the reason I'm not going to cancel it out here is it's going to save me from writing phosphorus every time with every conversion. Since I'm not going in between phosphorus and something else, I can save myself that little step right there. So that's my first step. My first step is I've turned the atoms into moles. Now I need to turn the moles into mass. The way to do that is to turn it into grams. And we would do that with molar mass. Now, grams and milligrams are not the same thing. So I know I've got one more step after this to turn the grams into milligrams. So moles in the denominator, grams in the numerator. Molar mass comes directly from the periodic table, 30.97. My moles cancel out in the process. I'm left with grams. Now, one important side note here. Get asked this question all of the time. How many decimal places do I carry from a molar mass reading off the periodic table? And the answer to that question is, it depends. How many significant figures do you need? We never want to be in the position where we have to round our answer because we didn't take enough digits off of the periodic table. Now, in this case, it doesn't matter. Our starting measurement is extremely rounded. It only has one sig fig. Here's the general rule of thumb I use. 2 decimal places. If I take the first 2 decimal places off of any of those mass readings on the periodic table, most of the time that gives me 4 significant figures. A couple occasions, if I'm working with some of the really light elements, it'll only give me 3. And maybe that's where I have to play with it in those circumstances. But usually that gives me 4. And for most of the stuff that we do, 4 significant figures is as many as we need. Because if you think of the mass readings that we take, our balances either read to 2 decimal places, which means I have either 4 or 5 digits, depending upon how heavy it is. Or if I'm using the really precise balance, maybe I have 5 or 6 because I have 4 decimal places, but by the time I do my subtraction, I only have 4 or 5 to work with. The point of the matter is 2 decimal places gives us most of what we need most of the time. It's a good rule of thumb. That's what a rule of thumb is there for, to kind of handle the what is your everyday kind of situation going to call for. You can take it beyond the 2 decimal places. It's not going to change your answer considerably. And so that's why I say round it off at 2. Now, if you need that 3rd decimal place because you've got something that's really precise and it has lots of significant figures, go ahead and use it. That's the exception, not the rule. Coming back to our problem, the last step is to convert the grams into milligrams. So there are 1,000 milligrams in every gram. My grams cancel out. Now I do my calculation. Multiply by everything on the top. Divide by everything on the bottom. 1 times 10 to the 30th. Multiplied by 30.97. Multiplied by 1,000. Divided by 6.022 times 10 to the 23rd. My calculator gives me this. 5.143 times 10 to the 10th. In fact, it gives me a lot more than this. I'm limited in this case by my initial measurement just says 10 to the 30th. Well, in scientific notation, that's 1 times 10 to the 30th. That's only 1 significant figure. So we would round that as so. So 5 times 10 to the 10th milligrams would be the correct answer there. So go ahead and put that answer into Top Hat so that you get credit. And do be advised that Top Hat is going to want scientific notation for this. The appropriate way to enter scientific notation is with a capital E. So 5, capital E, 10. would be the proper way to enter that number in scientific notation so that the programming algorithm knows what you enter and has done it properly. Right. Any questions with this example before we move on to an example I'm going to let you try on your own? All right, now the question I'm asking you to do on your own here is a little bit simpler. There aren't as many calculation steps because we're not starting with atoms this time. We're starting with moles. How many kilograms of lithium are in a 0.653 mole sample of that lithium? So take a moment here, work on your process, try to organize yourself. What steps do I need to do? What calculations do I have to do in what order? And then put your answer in. We'll come back and look at it in a couple of minutes. Yeah. for the most part, we are on the right track. Only things I was seeing, a couple of people had the wrong element. So you didn't grab lithium, you grabbed something else. The other thing that I saw was that last conversion. A lot of you had it flipped around. You know, kilogram is the bigger unit, so more grams pack into that kilogram than the other way. So 4.53 times 10 to the negative third. Would have been the correct value here for the number of kilograms of that lithium. All right. Any questions with this before we move on to just a couple of last little things before we call it a day? Okay, so we're going to buzz through a couple of sections real quick here, dealing with compounds and molecules. Now, this is stuff you probably already know. You already know what a chemical formula is. You already know that a chemical formula gives you that ratio between one atom and another, one element and another in that compound. We're going to get to the nomenclature of that stuff. That's the topic for Friday. But what we can do is, with that information about the chemical compound and what we know about Avogadro's number and this whole idea of moles, we can expand the kinds of conversions that we were just doing to more than just atoms. We can use chemical formulas to talk about them on the molecular level. We can also slide between the molecular level and the atomic level by using that chemical formula as well. So for example, if I have the compound propane, C3H8, well, one of those propane molecules has 3 carbons and 8 hydrogens. So if I know how many moles of propane there are, I know the number of moles of carbon because it'd be 3 times that. And I know the number of moles of hydrogen because it would be 8 times that. The chemical formula tells me so. From a molar mass standpoint, I also can know that these chemical formulas still correlate directly to that periodic table. The only thing that I have to do is account for that multiplicity. So for example, if I have calcium carbonate, I don't just simply take the molar mass of carbon and add the molar mass of calcium and the molar mass of oxygen. I have to take into consideration the chemical formula. Chemical formula says there is 1 calcium, 1 carbon, and 3 oxygens. So I would take the mass of the 1 calcium plus the mass of the 1 carbon plus the mass of the 3 oxygens and put them together to find the total mass of calcium carbonate, 100.09. For carbon dioxide, I would do the same thing. The mass of 1 carbon plus the mass of 2 oxygens to give me 44.01. For octane, I've got 8 carbons and 18 hydrogens. So I would take the molar mass of carbon and multiply it by 8, since there are 8 carbons in there. And I take the molar mass of hydrogen and multiply it by 18, since there are 18 hydrogens. Add all of that together, I get 114.26. So I can take this overall concept, which we started with kind of small, and I can expand it to larger molecules. I can expand it beyond just atoms and look at molecules, look at larger systems. That's what we're building toward. So on Wednesday, we're going to get into this last component here of the calculation section for chapter or for a module 2, talking about mass percent, talking about empirical formulas. Wednesday's lecture is going to be the last material that you'll see as far as what module 2's quiz is all about. So the nomenclature stuff that we're talking about on Friday, technically that's part of module 2, but it's not going to show up on the quiz. We're going to take those proficiencies first. You'll see that nomenclature stuff show up on a later module quiz. It's not going to show up here. In the meantime, go ahead and answer that stoplight question for today. And don't forget about your assignment that is due tomorrow night. Remember, it's a 2-pronged assignment. The calculation half is inactive. Don't forget about the feedback question top hat. You want to make sure you get all of the points, not just some of them. Have a great afternoon.